Ever stop to think about what happens in that blink of an eye when you type a website address into your browser and hit enter?
Oh, yeah. It feels instant, right?
Totally. But trust me, there's a whole universe of activity packed into that tiny moment. Welcome to the deep dive.
And we've got some really interesting stuff to unpack today.
We do. Insights from software engineering explain this, well, really fundamental process.
Think of it as a shortcut, maybe, to understanding the crucial steps, the surprising bits.
Exactly. Without getting totally lost in the technical weeds, our mission is pretty simple. Give you a clear, engaging picture of what's going on behind the scenes every single time you browse the web.
It truly is remarkable when you consider how often we do this. Just type, hit enter, done.
Without a second thought.
Right. But when you pull back the curtain, you find this incredibly orchestrated dance of tech.
So we're going to explore all that, from interpreting the address to secure connections and finally seeing the page.
That's the plan, the whole journey.
Okay, so let's start. You've typed in a URL, say https://www.example.com, and you hit enter. What's the very, very first thing the browser does?
Okay, so it immediately starts dissecting that URL, like a detective with clues.
Breaking it down.
Yeah, it looks at the scheme, the HTTPS part. That tells it the language, the protocol it needs.
HTTPS, so secure communication.
Precisely. Then the host name, www.example.com. That's the server it needs to find.
The where.
Exactly. And it notes the path, if there is one. And crucially for HTTPS, it knows the default port is 443.
Okay.
So it's basically mapping out where to go and how to talk once it gets there.
So the browser's got its plan, but before it just rushes out to connect, does it ever pause and think, hang on, have I been here recently?
Absolutely. Think of your browser as keeping notes, like a travel journal.
Okay.
It first checks its local HTTP cache. That's just storage space on your computer.
For stuff it already downloaded, like images and code.
Exactly. HTML structure, CSS styling, images, maybe JavaScript. It checks if it has a recent copy.
How does it know if it's recent enough?
Well, when the server originally sent those files, it included instructions, cache control headers.
Ah, right, like max age.
Yep, max age tells it how long it's good for. Or things like etag or last modified, which are like version numbers.
So it can check if the server's version has changed.
Correct. And if the browser finds a valid, fresh copy in its cache,
It just uses that, skips the network.
pretty much. The page loads super fast. It's a huge win for speed.
That's clever, a shortcut for frequent visits. But okay, what if it's a new site or the cache stuff is stale? What's next?
Right. Then the browser needs the server's actual digital address because www.example.com is for us humans.
Computers need numbers, right? IP addresses.
Exactly. So the browser needs to translate the name into that number. It's like looking up a contact in your phone.
Okay, so that's DNS resolution.
That's the one. DNS resolution.
So how does my browser find this number? It doesn't have, like, a giant phone book of the entire internet stored locally, does it?
Haha. No, not quite. It starts closer to home. First, it asks your computer's operating system.
The OS, Windows, Mac OS, whatever.
Yeah. The OS also keeps a little DNS cache if the OS doesn't have it.
Then it goes out onto the network.
Then it sends a query to what's called a DNS resolver. Often, this is a server run by your internet service provider, your ISP.
Or sometimes you can set it to use Google's DNS or Cloudflare's.
Exactly. You might use one of those public resolvers.
Okay, so this resolver, maybe my ISP server, it goes hunting for the IP address.
It does. The resolver kicks off a search. It usually starts by asking one of the root DNS servers.
Root servers, like the top level.
Kind of the ultimate authorities, yeah. They don't know the IP for www.example.com specifically.
But they know who might know.
Precisely. They know who handles the top-level domains, like .com. So the root server points the resolver to the .com TLD server.
Okay.
Then the .com server points the resolver to the authoritative name server for example.com.
Ah, the one that actually holds the record.
That's the one. That server finally provides the IP address. Could be IPv4, the older style, or IPv6, the newer one, sometimes both.
Got it.
And importantly, all these answers get pashed along the way. Your browser, your OS, the resolver itself.
To speed things up next time?
Exactly. It's a distributed system built for speed.
Wow, it really is like asking for directions layer by layer. Now, I've heard about DNS over HTTPS, DOH. What's that about?
Yeah, DOH, that's newer, and it's mostly about privacy.
How so?
Traditionally, those DNS lookups, asking for the IP address, they were sent unencrypted. in the clear.
Meaning someone on the network could see what sites I'm trying to visit.
Potentially, yes.
Yeah.
DOH encrypts those requests, usually by sending them over an HTTPS connection to a special DOH resolver.
So it hides the lookup itself.
Right. Makes it much harder for others on the network to snoop on your browsing habits.
Makes sense. Privacy is key. Okay, so recap. We parsed the URL, maybe used the cache, or otherwise got the IP address via DNS. Now what?
Now, finally, it's time to actually talk to the server at that IP address. We need to establish a connection.
And for most web stuff, that's TCP.
Yep. Transmission Control Protocol, TCP. It's the reliable way computers set up a conversation online. It starts with the famous three-way handshake.
Okay, walk me through that.
Your browser sends a little message called SYN to the server. Think of it as, hey, can we talk?
SYN, got it.
The server, if it's listening, replies with SYN ACK. That's, yes, I heard you and I want to talk to you.
Acknowledging and initiating back.
Right. Then your browser sends one final message, ACK. Okay, I heard your confirmation, let's talk.
SYN, ACK, ACK, 3 steps.
And that establishes the TCP connection. Both sides know the other is ready. The speed of this depends on your network, of course. Latency, congestion.
Right, but we were talking about HTTPS earlier. That SYN means secure. Does that happen now?
Exactly. If the URL is HTTPS, then right after that TCP handshake finishes, another handshake begins. The TLS handshake.
TLS, Transport Layer Security.
That's the one. This is where the encryption gets set up.
Okay, how does that work? More messages.
Yep. Your browser sends a client hello. It basically says, hi, I want a secure connection. Here are the encryption methods I know. It lists cipher suites and includes a random number.
Offering options.
Then the server replies with server hello. It picks one of those cipher suites, says, okay, we'll use this one, and sends back its digital certificate.
The server's ID card you mentioned.
Exactly. Signed by a trusted certificate authority, a CA.
And my browser checks that, like verifying the ID.
It does. It checks the signature against its list of trusted CAs.
Yeah.
If it's valid, not expired, matches the domain name. All good.
Okay.
Then comes the key exchange. This is the really clever crypto part. Using methods like ECDHE, the browser and server figure out shared secret keys without actually sending the keys themselves over the network.
Wow. Magic math.
Pretty much. Once they both have these shared secret keys, boom, secure session established, all future communication is encrypted.
And that protects my data.
Absolutely. And modern TLS, like 1.3, has optimizations like 0 RTT to speed this up for return visits. Plus, there's TCP fast open, trying to cut down that initial TCP handshake time too.
So much going on just to get connected securely. Okay, connection established, secure channel open. Now can the browser ask for the web page?
Now it can. The browser sends an HTTP request, usually a GET-D request.
Just get this page.
Basically, yeah.
Yeah.
Get or get some path, but it also sends a bunch of headers along with it.
More headers. What kind of info?
Important context for the server, like the host header essential if one IP hosts multiple sites tells the server which site you want.
Oh.
User agent tells the server about your browser and OS. Accept says what content types you understand, HTML, images.
Except encoding. Is that for compression?
Yep, like gzip or brotli. Tells the server it can send back smaller files. Connection.keepalive asks to reuse this connection for more files.
Saves setting up new connections for every image and script.
Exactly. Referer might say where you clicked from. And cookie. That's a big one.
Cookies. For remembering logins and stuff.
Right. If the server previously gave your browser a cookie, it sends it back now. Helps maintain your session, preferences, etc. Sometimes security tokens, too.
And this whole request might be using newer HTTP versions, like HTTP 2.
Could be. HTTP 2 or even HTTP 3 using QUIC. They're more efficient, handle multiple requests better over that single connection.
Okay, so this detailed request, packed with headers, hits the server. What happens there? It's not just one machine usually.
Almost never for big sites. Your request probably hits a load balancer first.
A traffic cop.
Good analogy. Like in Jinx or maybe in AWS ELB, it spreads the incoming requests across many backend servers.
So no single server gets overloaded.
Right. And the load balancer might even handle that TLS decryption SSL termination, they call it.
Before passing the plain request to the actual web server.
Often, yeah. Behind the load balancer, you've got the web servers themselves, maybe running in containers like Docker.
Managed by something like Kubernetes.
Quite possibly. And those servers run the actual website application using frameworks like Express.js, Django, Rails, whatever the site is built with.
And that's where the site's logic runs.
Yes. It processes your request. Maybe it needs to talk to a database SQL or NoSQL to fetch your user info or content.
Or check a cache, like Redis.
Could be. Fetching data from an in-memory cache like Redis or Memcached is way faster than hitting the database every time.
So it gathers all the necessary data.
Runs its code, figures out the response, and assembles the web page content for you. It's quite an orchestration.
Mind-boggling coordination just for one page view.
Yeah.
Okay, server does its work. What does it send back?
It sends back an HTTP response. First thing is the status code.
200. Okay, hopefully.
That's the goal. But you might get others. 301 moved permanently if the page moved.
404 not found. The classic.
Yep. Or 500 internal server error if things went wrong on their end.
Okay, status code first. Then what?
More headers. Response headers. These tell your browser about the data coming its way.
Like content type. To say if it's HTML or JSON or an image.
Exactly. Content length tells the size. Cache control, again, instructions for your browser on caching this response.
E-tag for versioning.
Right. Set cookie if the server wants to store or update a cookie in your browser.
Course headers.
Yes,
Security stuff.
yeah, cores for cross-origin requests, plus other security headers like content security policy to prevent certain attacks.
And then finally, the actual content.
Then the payload. The HTML code or JSON data or image bytes, whatever you asked for.
And maybe compressed?
Often, yes. Using gzip or brotli, indicated by the content encoding header, saves bandwidth, speeds things up.
What if it sends back a 301 redirect?
Ah, good point.
Right.
If it's a 3xx redirect, the browser sees the new URL in the location header and basically starts the whole process over again for that new address.
Right, go fetch that URL instead. Okay, so finally,
Yeah.
after all that, the browser gets the payload, maybe some HTML code. But it's
Yeah.
still just code, right? Not a visual web page.
Correct. Now the browser's rendering engine kicks in, it gets that HTML,
And starts building
starts parsing it, building the document object model.
the blueprint you mentioned.
Exactly. A structured tree representing all the HTML elements, headings, paragraphs, images, links.
Does it just read top to bottom?
Mostly, but as it parses, if it hits links to external resources, especially in the head, like CSS files,
For styling?
yeah, or JavaScript files for interactivity,
Okay.
it might pause parsing the HTML.
Pause. Why?
To go fetch and process those files first, they're often blocking resources. The browser needs the CSS to know how to style things and potentially the JavaScript to manipulate the structure before it displays the final page.
Ah, so fetching those can delay actually seeing the page.
Definitely. Once the DOM is built and the CSS rules are figured out, that's the CSSOM, another tree structure, the browser combines them to calculate the layout where everything goes on the screen.
Figures out positions and sizes.
Right. And then finally, it paints the pixels onto your screen. You see the web page.
Wow. It really is an incredible journey, isn't it?
Absolutely phenomenal.
From typing a few characters to, well, all of that. DNS lookups, handshakes, requests, server logic, rendering, happening in fractions of a second.
It really highlights this vast, intricate web of technologies working together, stuff we totally take for granted.
Every single day.
It's a real testament to, decades of engineering and collaboration that built this whole system.
So thinking about all these steps, it really makes you wonder, right? What parts of this process do you think have the biggest impact on, say, website speed, on performance?
That's a great question.
Or maybe, if you're building web apps, how does knowing this whole flow change how you might approach development? Or even just fix things when they break?
Yeah, understanding the bottlenecks, the potential delays. It definitely informs how you build or troubleshoot.
Absolutely. Definitely some food for thought for everyone listening the next time you click a link or type in that URL.